15 billion miles from Earth, a machine the size of a compact car is doing something that defies belief. It's transmitting a radio signal with the power of a refrigerator light bulb. And we're receiving it. Not just receiving it. We're decoding complex scientific data. We're sending commands back across that impossible distance. And the spacecraft is executing those commands. Every physicist who examines the math says the same thing. This shouldn't be possible. The signal is too weak. The distance is too vast. The laws of physics should have swallowed this transmission in noise decades ago. And yet, right now, at this very moment, Voyager 1's signal is traveling through the void, crossing space so empty that there's less than 1 atom per cubic centimeter, taking 22 hours and 36 minutes to reach us. This is more than communication. This is a lifeline, the most improbable connection ever established. And NASA is fighting every single day to keep it alive, because the clock is ticking, and that lifeline is getting thinner. Let's talk about the fundamental problem, the physics problem that makes every engineer shake their head in disbelief when they see Voyager still working. Radio signals degrade with distance. This isn't negotiable. It's called the inverse square law, and it's one of the most ruthless principles in physics. Here's how it works. When you double your distance from a radio source, the signal doesn't drop to half strength. It drops to 1/4 strength. Triple the distance? The signal becomes 1/9 as strong. 10 times farther? 1/100th the strength. Now scale that to 15 billion miles. Voyager's main transmitter puts out 22.4 watts of power. That's roughly equivalent to the light bulb in your refrigerator. Not much. But when Voyager launched in 1977, that was considered adequate for the mission. Nobody expected the mission to last this long. Nobody expected Voyager to get this far. By the time that 22.4-watt signal travels 15 billion miles, it arrives at Earth with approximately 0.002022221 watts of power. Let me write that out. That's 1 times 10 to the negative 20th watts, 100 quintillionth of a watt. To put this in perspective, if you somehow collected every single photon of radio energy that Voyager 1 has transmitted over its entire 46-year mission and combined all of that energy into a single burst, the total wouldn't provide enough power to run a basic digital wristwatch for more than a few seconds. That's what NASA is trying to detect. Every single day. A signal so faint it's almost indistinguishable from the background radiation of the universe itself. So, how is it possible? The answer involves the largest movable structures on Earth, receivers cooled to near absolute zero, signal processing algorithms that border on science fiction, and a level of precision that leaves almost no margin for error. Let's start with the antennas. NASA operates something called the Deep Space Network, or DSN. It consists of 3 complexes positioned strategically around the globe. One is in Goldstone, California, in the Mojave Desert, middle of nowhere, chosen specifically because it's far from cities, far from radio interference, surrounded by mountains that block stray signals. The second is near Madrid, Spain. Similar setup, remote location, minimal interference. The third is near Canberra, Australia. These 3 locations are spaced approximately 120 degrees apart in longitude. This isn't random, it's deliberate. As Earth rotates, spacecraft move across the sky. A single antenna facility would lose line of sight as the spacecraft sets below the horizon. But with 3 facilities spaced around the planet, at least one always has line of sight to any deep space probe. The network provides continuous 24-hour coverage. This is critical for Voyager, because if we lose the signal even temporarily, reacquiring it becomes incredibly difficult. Each facility has multiple antennas, small ones for closer spacecraft, medium ones for Mars missions. And then there are the giants, 70-meter dishes. That's 230 feet in diameter. These aren't satellite dishes. They're not even close to what most people imagine when they think of antennas. Standing at the base of a 70-meter dish feels like standing next to a skyscraper that's been tilted on its side. The structure weighs nearly 3,000 tons. The surface area of the dish is over 38,000 square feet. And yet, despite this massive size, the parabolic surface is machined to an accuracy of less than 1 millimeter across the entire span. Why does that matter? Because radio waves are incredibly small. Voyager transmits at a frequency of about 8.4 gigahertz. At that frequency, the wavelength is roughly 3.6 centimeters. If the dish surface has imperfections larger than a fraction of that wavelength, the incoming signal scatters. Precious photons bounce off in wrong directions. Signal is lost, so the dish must be nearly perfect. And it must stay perfect even as it moves. These dishes can rotate. They track spacecraft as they move across the sky. The entire 3,000-ton structure pivots on bearings, following Voyager's position with precision down to 1/100th of a degree. When Voyager's signal reaches Earth, it's spread across a vast area. The radio waves have been expanding outward in a sphere for 15 billion miles. By the time they reach Earth, that sphere is so large that the portion of the signal hitting our planet is infinitesimal. The 70-meter dish acts like a giant funnel. It collects all the radio waves hitting its surface and concentrates them into a single focal point. But even with a 230-foot antenna capturing the signal, what arrives at the focal point is still almost impossibly weak. This is where the receivers come in. The collected signal gets fed into what's called a low-noise amplifier. But calling it an amplifier doesn't do it justice. This device is cooled to approximately 4 Kelvin. That's negative 269 degrees Celsius, just 4 degrees above absolute zero. Why so cold? Because heat is noise. At normal temperatures, atoms vibrate. Electrons move randomly. This creates electrical noise that can completely drown out faint signals. At 4 Kelvin, atomic motion nearly stops. The thermal noise drops to almost nothing. The signal then passes through a series of amplifiers. Not regular amplifiers. These use technology called high electron mobility transistors, or HEMTs. They can amplify signals by a factor of billions without adding significant noise of their own. Think about that. Billions of times amplification, with minimal distortion. After amplification, the signal goes into digital signal processors. These are computers running algorithms specifically designed to extract Voyager's transmission from background noise. The processors know exactly what Voyager's signal should look like: the frequency, the modulation pattern, the timing. They compare the incoming data against these expected patterns, filtering out anything that doesn't match. It's like having a conversation in a stadium full of screaming people. You know your friend's voice, you know the rhythm of their speech. So even though there's chaos all around, you can pick out their words. That's what these processors do. Except the stadium is the entire universe, and the screaming is cosmic background radiation, solar interference, and random noise from every direction. And somehow, it works. But here's where it gets even more complicated. Voyager isn't stationary, it's moving. Right now, Voyager 1 is traveling at approximately 38,000 miles per hour relative to the Sun. That's 17 kilometers per second, about 11 miles every single second. This motion creates what's called Doppler shift. You've experienced this with sound. An ambulance approaches with a high-pitched siren, then drops to a lower pitch as it passes and moves away. The same thing happens with radio waves. As Voyager moves away from Earth, its radio signal gets stretched. The frequency drops slightly. The shift is tiny, but at the sensitivity levels we're working with, tiny matters. NASA has to account for this constantly. The Deep Space Network receivers aren't tuned to a fixed frequency. They're constantly adjusting, tracking Voyager's Doppler shift based on its known velocity and trajectory. But there's more. Earth is also moving. We're rotating on our axis, orbiting the Sun, and the Sun itself is moving through the galaxy. All of these motions add up. They all affect the Doppler shift. NASA has to calculate all of it, predict where Voyager will be at the exact moment the signal arrives, adjust for Earth's position and motion, compensate for relativity effects. Get any of this wrong, and the signal disappears into noise. But NASA has been doing this for 46 years. They know Voyager's trajectory better than almost anything else in the solar system. They can predict its position years in advance, accurate to within a few kilometers. Except when something goes wrong. And things do go wrong. In August 2023, Voyager 2 vanished. Engineers were performing a routine command sequence, updating some parameters in the spacecraft's attitude control system, standard procedure, done hundreds of times before. But this time, something went wrong. A command was misinterpreted or executed slightly differently than expected. Nobody knows exactly what happened. What they do know is that Voyager 2's antenna shifted by 2 degrees. 2 degrees? That doesn't sound like much. A 2-degree error. Tiny, right? But Voyager's transmitter doesn't broadcast in all directions. It can't. The signal would be far too weak. Instead, the 12-foot dish antenna focuses the transmission into a narrow beam, less than half a degree wide. This concentration is what makes communication possible. All of Voyager's limited power focused into a tight cone aimed directly at Earth. But it means the aim has to be perfect. When the antenna shifted 2 degrees, Earth moved completely outside that beam. The signal stopped. NASA's Deep Space Network antennas, all 3 facilities, heard nothing. Silence. Mission control at NASA's Jet Propulsion Laboratory went into crisis mode. They couldn't send commands to fix it. Because Voyager couldn't hear them. The spacecraft's receiver was also directional, and it was no longer pointed at Earth. They were cut off. Completely. Engineers immediately began calculations. How much power did Voyager have? How long could it survive without instructions? What were the options? And then someone remembered the backup system. Decades ago, when Voyager was designed, engineers anticipated that orientation errors might occur. So they programmed an autonomous reset feature into the spacecraft's software. Several times each year, Voyager automatically checks its own orientation. It uses star positions to determine which way it's pointing. If it detects significant drift, it triggers an automatic correction sequence. But there was a problem. The next scheduled reset wasn't for several weeks. All NASA could do was wait. Days passed, then a week, then 2 weeks, and then, exactly when the calculations predicted, Voyager 2's signal reappeared. The spacecraft had executed its automatic reset, corrected its orientation, repointed the antenna at Earth, all on its own, billions of miles from home, with no human intervention, communication restored. But the incident revealed just how fragile this lifeline really is. How many things have to go exactly right? A 2-degree error. That's all it took to nearly lose Voyager forever. And there are so many other failure points. Take the thrusters, for example. Voyager uses a set of 16 small thrusters to maintain its orientation. Each one is tiny. They produce just 0.8 newtons of force. That's roughly the weight of a tennis ball. But in the vacuum of space, even this tiny force is enough to rotate the spacecraft slowly, keeping the antenna pointed at Earth. The thrusters run on hydrazine fuel. They fire in short pulses, milliseconds at a time. Little bursts to nudge the spacecraft's orientation. Over 46 years, these thrusters have fired millions of times. And there's a problem developing. Hydrazine, when it combusts, leaves behind a residue, tiny amounts. But over decades, that residue accumulates inside the fuel lines and valves. It's like plaque building up in arteries. Eventually, that residue will clog the system. The valves will stick. The thrusters will become unreliable. And when the thrusters fail, Voyager will start to tumble. Once it starts tumbling, there's no recovery. The antenna will drift off target. The signal will be lost. NASA knows this is coming, so in 2017, they did something remarkable. They fired a set of backup thrusters that hadn't been used in 37 years. Voyager has two sets of thrusters. The primary set, which had been used for decades, was showing signs of degradation. So engineers wrote new software, uploaded it to Voyager, and switched to the backup thrusters. It worked. The backup thrusters fired perfectly. Then, in 2020, they reprogrammed the thruster control system again. Instead of firing many short bursts, the new software fires fewer, longer pulses. This reduces the number of times the valves open and close, which slows down the accumulation of residue. The change bought approximately 5 more years of thruster life. But it's a temporary fix. Eventually, both sets of thrusters will fail. There's no way around it. When that happens, the mission ends. But thrusters aren't the only concern. There's also power. Voyager doesn't have solar panels. At its current distance, the Sun appears as just a bright star. Sunlight is about 3,600 times fainter than it is on Earth. Solar panels would be useless. Instead, Voyager runs on nuclear power. Each spacecraft carries 3 radioisotope thermoelectric generators, or RTGs. These are cylindrical devices about the size of a small barrel. Inside each RTG are pellets of plutonium-238. Not the kind used in bombs. This is a different isotope. It's not fissile. It doesn't undergo chain reactions, but it does decay. Radioactive decay. And that decay produces heat. A lot of heat. About 2,000 watts of thermal energy from each RTG. That heat flows through thermocouples, devices that convert temperature differences directly into electricity. It's not efficient. Only about 7% of the heat becomes electricity. But it works, and it's reliable. At launch in 1977, Voyager's 3 RTGs produced a combined 470 watts of electrical power. That was enough to run all the instruments, all the computers, the transmitter, heaters, everything. But plutonium-238 has a half-life of 87.7 years. This means that every 87.7 years, the heat output drops by half. And as heat output drops, electrical power drops. After 46 years in space, Voyager's RTGs are now producing less than 220 watts of power. And the decline continues. Roughly 4 watts are lost every year. NASA has been managing this power crisis by shutting down systems one by one. Triaging, deciding what's essential and what can be sacrificed. In 1990, after Voyager 1 completed its tour of the outer planets and photographed Saturn's moon Titan, NASA made a difficult decision. They commanded the spacecraft to turn around one last time, point its cameras back toward the inner solar system, and take a final photograph of Earth. From a distance of 3.7 billion miles, Earth appeared as a tiny speck, less than a single pixel. a pale blue dot suspended in a beam of scattered sunlight. Carl Sagan, one of the scientists who advocated for the Voyager missions, later wrote about that image. "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives." It was the last picture Voyager 1 ever took. After that photograph, the imaging system was shut down permanently. The cameras have been off for 34 years. They will never turn on again. Power saved, about 7 watts. Other systems followed. The ultraviolet spectrometer, off in 2016. The plasma science instrument on Voyager 1, off in 2007 after the instrument failed. Heaters for various components, shut down one by one, even though it means those components now operate far below their designed temperature range. Right now, Voyager 1 has only 4 functioning science instruments. The magnetometer, measuring the strength and direction of magnetic fields in interstellar space. The low-energy charged particle detector, the cosmic ray detector, and the plasma wave instrument, which studies the density and composition of the plasma between stars. These 4 instruments are sending back data that has never been collected before. Information about a region of space no human-made object has ever reached. But even these are living on borrowed time. NASA estimates that by 2025, they'll need to shut down 1 more instrument, probably the cosmic ray detector. Then, around 2028, another will have to go. By 2030, maybe 2 instruments will still be running. By 2032 or 2033, there likely won't be enough power to operate any science instruments at all. At that point, Voyager will switch to transmitting only engineering data: its temperature, its orientation, system status. This mode requires less power. It might allow the spacecraft to continue transmitting for a few more years. But eventually, even that will become impossible. NASA's current best estimate is that Voyager 1 will have enough power to maintain communication until approximately 2036, 13 years from now. After that, the transmitter will shut down. Not because it's broken, but because there isn't enough electricity to run it. The signal will stop, and Voyager will go silent. But power isn't the only thing that could end the mission early. There's also the threat of damage. Space is not empty. Even interstellar space. There are dust grains out there, tiny particles. Most are smaller than grains of sand. Some are just molecules clumped together, but they're moving fast. Relative velocities can reach tens of kilometers per second. At those speeds, even a microscopic particle carries significant kinetic energy. A dust grain the size of a grain of table salt, hitting Voyager at 20 kilometers per second, impacts with the energy of a bullet. Voyager has some protection, a debris shield in front of the main body. But it's not comprehensive. A particle could hit the antenna, puncture a fuel line, damage the transmitter, strike a critical computer component. So far, Voyager has been lucky. In 46 years of travel, it hasn't suffered any catastrophic impacts. But every year, the odds get slightly worse. There's also radiation, cosmic rays, high-energy particles from exploding stars, black holes, and other violent cosmic events. They zip through space at nearly the speed of light. When a cosmic ray hits a computer chip, it can flip bits in memory, corrupt data, crash systems. This is called a single-event upset, and it's a constant threat to spacecraft. Voyager has already experienced this. In 2023, Voyager 1 started sending garbled data. Complete nonsense. Engineers spent months diagnosing the problem. They eventually traced it to a corrupted memory chip in the flight data system, one of Voyager's 3 onboard computers. The chip had probably been hit by a cosmic ray. A single high-energy particle flipped some bits, corrupting the code the computer was using to package science data. NASA couldn't replace the chip. Obviously. Voyager is 15 billion miles away. So they got creative. They uploaded new software. Instructions telling Voyager to route data through a different section of memory, bypassing the corrupted chip. It took weeks to write the code, more weeks to test it, then 22 hours to transmit it to Voyager, then 22 hours to get confirmation back. But it worked. The corrupted data stopped. Clean signals resumed. But here's the terrifying part. That was luck. If the cosmic ray had hit a different chip, one that couldn't be bypassed, the mission might have ended right there. And it could happen again, any time. There's also the problem of signal strength continuing to decline. Even if nothing breaks, even if Voyager keeps working perfectly, there's a hard physical limit approaching. As Voyager moves farther away, the signal gets weaker. Every single day. The Deep Space Network antennas are already operating at the absolute edge of what's possible. The receivers are cooled to near absolute zero. They're using the most sensitive amplifiers that physics allows. There's no more room to improve on the receiving end, which means, at some point, Voyager's signal will simply drop below the noise floor. We'll be listening. The antennas will be pointed at exactly the right spot. Everything will be working. But we won't hear anything. Just static. Background radiation. Noise. And we won't know if Voyager stopped transmitting or if the signal just became too faint to detect. NASA estimates this will happen around the same time the power runs out. Mid-2030s. But it could happen sooner. A solar flare could increase background noise temporarily, drowning out the signal for days or weeks. Or interference from Earth could become too severe. As our planet fills with more wireless devices, radio pollution increases. The Deep Space Network facilities are in remote locations specifically to avoid this. But there's only so much isolation possible. So we have, at most, 13 years left, possibly less. Every day that Voyager's signal reaches Earth is a small miracle. And NASA is fighting to extend that miracle as long as possible. Engineers monitor the spacecraft 24 hours a day, 3 shifts, around the clock. They track every parameter: power levels, thruster performance, temperature, signal strength. They plan years in advance. Which instruments to shut down when. How to squeeze the maximum science out of declining power. They write software patches for 46-year-old computers. They solve problems across billions of miles with weeks-long communication delays. And they know that no matter what they do, the end is coming. One day, the signal will stop. Voyager will still be out there, still traveling at 38,000 miles per hour, still moving deeper into interstellar space. In about 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445. It won't stop. It won't slow down. It will simply drift past, a silent messenger from a distant world. If it's ever found, if some other intelligence ever intercepts it, they'll discover the golden record attached to its side. Sounds from Earth. Music. Greetings in 55 languages. Images encoded in analog format. Instructions on how to play the record, etched onto the surface in symbols. A message in a bottle. Thrown into an ocean larger than comprehension. But for now, Voyager is still ours. We can still hear it. That impossibly faint signal, crossing 15 billion miles, carrying data from the edge of everything we know. A 22-watt transmission that shouldn't be detectable. That defies the inverse square law through sheer engineering brilliance. Every photon that reaches Earth is precious. Every byte of data is irreplaceable. And every day that the lifeline holds is a testament to human ingenuity. This is Voyager 1's lifeline, 15 billion miles long, impossibly fragile, and still, somehow, miraculously, alive.